Hi everybody, Mrs. Pesic here. We are looking at Chapter 2, Geometric Reasoning, and you're doing Section 2.1, using inductive reasoning to make conjectures. So while you're watching this video, you should be completing your guided notes, which in this case would be considered video guided notes. And while you're doing that, you may want to stop the video to copy something down. You can pause the video. You certainly can rewind the video. However you need to interact with this video so that you're understanding this section and so that you're completing your video guided notes. So section 2.1 is using inductive reasoning to make conjectures. And your goals are to use inductive reasoning to identify patterns and make conjecture, and also to find counterexamples to disprove conjectures. So first of all, let's start with some examples. We're looking for patterns here. Can you find the next item in each pattern, and can you explain what your reasoning is? So for example, if you saw a pattern that goes Monday, comma, Wednesday, comma, Friday, what do you think would be the next item in the pattern? Well, some of you might say, the next day, it looks like they're going every 2 days, so 2 days after Friday would be a Sunday. So you might say that, and your reasoning would be because, I'm abbreviating, because it skips a day, or because it goes every other day. All right? What about this next example? I've got this pattern, 3, 6, 9, 12, 15, dot, dot, dot. What would be the next item in this pattern? Well, you might say, it looks like the next pattern, it looks like the next item would be 18, and you could say because it's going up by 3. It goes up by 3 each time. All right, and what about this last example? We see a bunch of arrows here. One is going straight to the left. One is going kind of halfway to the left, halfway up. So I guess I could say, oh, this one looks like it's pointing west. This one looks like it's pointing northwest. This one looks like it's pointing north. Well, what would be the next one in the pattern? Maybe it would be heading off at an angle like this. So that would be kind of like heading northeast, maybe. All right, and you could say, oh, it looks like this is going to be the next item because it looks like it's going, you know, it keeps advancing by 45 degrees each time, or it keeps advancing from, you know, the directions north, northwest, west, northwest, north, and then northeast, and so on. Let's take a look at the next item here. So inductive reasoning is the process of reasoning that a rule or statement is true because specific cases are true. And so if you need to pause this video to write that down, go ahead and do that. Okay, so inductive reasoning, to help you remember inductive reasoning with a big capital I, think of it as I see, I observe, I notice. So these are just kind of observations that you're making, and you're kind of coming up with some kind of a statement about what you're observing. So is it true all the time? Not necessarily. So maybe it's true, maybe it's not. All right, so that's just inductive reasoning. So what is a conjecture? Again, if you need to pause the video, go ahead and do that. A conjecture is a statement you believe is true based on your inductive reasoning. So things you observe and patterns that you notice. That would be an example, that would be a conjecture. So conjectures are not necessarily true or false. They're something that we try to prove true or try to disprove as false. So conjectures aren't true or false. They're something we aim to prove or disprove. All right? So if you're not finished copying things down, go ahead and pause this video, and I'm moving on to the next page. Okay, so let's complete this conjecture. The product of an even number and an odd number is what? We're trying to make a conjecture now. So if we're going to take the product of an even number, I'm just going to pick an example of an even number like, let's say, 6, and an odd number, let's say 5, when I multiply those, now multiply because it says product, what do I get? Well, 6 times 5 is 30, so I'm getting what kind of a number? Well, I'm getting an even number. Does that happen all the time? Let's try a couple more examples to see if that's always going to be true. Let's pick a different even number like 2 and a different odd number like 7. Well, 2 times 7 is 14. That's an even number. Let's try one more example. What about if we pick an even number like 8 and an odd number like 1? Well, 8 times 1 is 8. That's even, so it sure looks like every time we take an even number and odd number and multiply them together, the product is even. So that's our conjecture. Did we prove that conjecture is true? No. We're just making a statement that we think is true based on some observations of specific cases. So this is an example of a conjecture. All right, let's take a look at, where are we at? We're right here. Take a look at this example. It says the number of segments formed by n collinear points is what? So let's take a look at this example. We have a segment drawn here with 2 points on it. So how many segments are formed? Looks like just one segment is formed. Just this one right here, just one segment. All right, what if we take a look at this next example? Here we have actually 3 points drawn that are collinear. So how many segments? Well, you might say, here's one segment and one segment, that's 2 segments, but don't forget we still have this whole segment, so that's another segment. So really we have a total of 3 segments in that picture. What about if we had 4 points drawn, 4 collinear points? Well, how many segments are formed here? Well, it looks like we would have 1, 2, 3, but then we could have taken this one right here, that's another one, or this one right here, that's another one, and don't forget we have the whole one also, so that one would be another one, so that looks to me like a total of 6 segments. And what about if we have this one with 5 points on it? So again, we have this one is 1, 2, 3, 4. This is 5 points, so we've got 4 little segments. And how many segments do we have that are kind of like this medium length? Well, there's one, and then from here to here is another one, and then from, there's a different color here, then from here to here is another one. So far we've got 7, but we could have also had these larger segments that were, we kind of clear all this out. We could have also had, here's my original here, we could have also had, let me erase this, these ones that are this long. So there's one of those, and then there's another one of those. So that's another one and another one. And then lastly, we could have had the whole one that was this long. So that was how many altogether? 1, 2, 3, 4, 5, 6, 7, 8, 9 segments. Let's see if that's going to be working out okay. Actually, I think I missed one. I think there was 10. Let's try this again. So if I have this, I've got the little ones, which would be 1, 2, 3, 4. So there's 4 little ones. And then I would have, let me get rid of those, and then we could have 4, let's see, how many of these that are 2 units long? There's one, and then here's another one, and here's another one. So that's 3 of those. All right. So I got that. That's 3. And then what about if we clear that out of the way, clear that out of the way, clear this out, and then what if we have one that is 3 units long? There's one of those, and here's another segment that's 3 units long, so that's 2 of those, right? And then I could have the original full length, which goes from here all the way to here. So that would be just one of those. So if I add those up, that looks like it actually equals 10. So, wow, without having to do this again, because that was rough, can we make a conjecture about how we could find the number of segments formed if, let's see, if I added one more row to this. If I say 6 points That's going to be how many? Well, let's back up. How could we have gotten, we see how we got 10. It was, there were 5 points, and so we did 4 plus 3 plus 2 plus 1. So what if there were 4 points, right? If there were 4 points, then we ended up getting 6, but maybe we could have found that by doing 3 plus 2 plus 1. That would give us 6. And how could we have gotten 3 segments if there were 3 points? Are you seeing a pattern here? That one might have been just 2 plus 1 gives us 3. And lastly, we just had 1 because there were 2 points, there was 1. So can we make a conjecture here? I'm hoping you're getting the idea that if there were 6 points, instead of 4 plus 3 plus 2 plus 1, it would be 5 plus 4 plus 3 plus 2 plus 1. And so that would give us 15 for the next one. So that's kind of our conjecture. The number of segments formed by n collinear points is, slide this down here so I can write on this. So the number of segments formed by n collinear points would be really, we'd have to add up all of these, it's be the sum of all the whole numbers. Let's write it that way. It would be the sum of all the whole numbers less than n. Less than n. All right. So that's how we could say that. So if we wanted to say, oh, how many, if we make a segment with 10 points on it, how many segments would it be? Well, it would be the sum of all of the whole numbers that are less than n. So we start with 9 plus 8 plus 7, and we keep going all the way down to plus 2 plus 1, and we get our answer. So that's our conjecture. Did we prove it? No, but that's just our conjecture. Okay, let's take a look at this example. To learn about the migration behavior of California gray whales, biologists observed whales along 2 routes. For 7 days, they counted the number of whales seen along each route. So make a conjecture based on the data. So the direct route, on the first day, we saw 1 whale. On the second day, 3 whales. On the third day, 0 whales. Then 2 and 1 and 1, and then none on the last day. I'm not seeing any pattern there with those numbers. What about the shore route? On the first day, they observed 7 whales. Then 9 whales, then 5, then 8, then 8, then 6, then 7. Again, I don't see a lot of, I don't see any pattern going on here. So for this one, I think the only thing maybe that we could say is, our conjecture could be there will always be more whales seen on the shore route. Maybe that's all we can say. But that would be our conjecture. Is it true? Who knows? We would have to, test this for every day for, a long time. And even then, we might not be proving this conjecture. But we're just making a statement based on what we see. All right. So remember, conjectures are not true or false. They're just something that we aim to prove or disprove. To prove a conjecture is true, you have to show it's true for all cases. So this is really important. To prove a conjecture is true, you have to show it's true for all cases. All right, but to prove a conjecture is false is a lot easier because you only have to find one example that isn't true, and we call that a counterexample. So here's the steps in inductive reasoning. The first step is that you look for a pattern. You try and find out what's happening, what's the pattern going on. Then step 2 is to make a conjecture, make a statement about what you're seeing. And then the third step is to either prove the conjecture or find a counterexample that would disprove the conjecture. So let's take a look at an example of trying to disprove something, trying to show it's false, by finding a counterexample. So in this example, it says, for all positive numbers n, 1 over n is always going to be less than or equal to n. Is this statement true or not? 1 over n is always less than or equal to n. Well, let's try a few examples. Let's say n was equal to 4. Then if I plug in 4 here and 4 here, do I get a true statement? 1 over 4 is less than or equal to 4. Is that true? Yes. So is that a counterexample? No, that's just an example of it actually happening. Does that prove that it's true all the time? No. Let's try a different n value. What if I choose n equaling 1? Well, if I plug in 1 here and here, I'm going to have 1 over 1 is less than or equal to 1. Well, 1 over 1 is just 1, so I get 1 is less than or equal to 1. Is that true? Well, actually, 1 is less than or equal to 1 because it's got the equals part, so that's true. So that's not a counterexample. Let's try another one. What if we pick something that's, it's got to be a positive number, but they didn't say here that it had to be an integer. What if we took a fraction like 1/2? So if I try n equaling 1/2, I'd have to say, I'm going to plug in 1/2 now, 1/2 here and 1/2 here. So I'd have 1 over, I'm going to have, let's start this again. I'm going to have 1 over 1/2 is less than or equal to 1/2. Is that true? Well, 1 over 1/2 is the same as 1 times 2 over 1. So that's equal to 2. And is 2 less than or equal to 1/2? Oh, that's a no. So we found a counterexample. So we can say n equaling 1/2 is a counterexample to this statement that 1 over n is always less than or equal to n. So 1 over n less than or equal to n is false. You only have to find one counterexample, and our counterexample is 1/2. Only have to find one counterexample to show that a statement is false. All right, let's try this one. Show that this conjecture is false by finding a counterexample. I'm going to leave that one for a little bit. So this first one says, for any real number x, x squared is always going to be greater than or equal to x. Well, let's try a few values, like let's say x equals 3. If I plug that in for x here and here, I would get 3 squared is greater than or equal to 3. So 9 is greater than or equal to 3. Well, that's true. So that's not a counterexample. Let's try another example. What about if we choose like x equals 1? Well, and then I'd have 1 squared is greater than or equal to 1, but that's the same as saying 1 is greater than or equal to 1, and that's true. So that's not a counterexample. What if I try a negative number? Like, let's say I try x equals negative 4. Well, then I'd have negative 4 in parentheses squared is greater than or equal to negative 4. Is that true? Well, yeah, because I get 16 is greater than or equal to negative 4. So that's true. So far, no counterexample. Maybe one doesn't exist. Well, let's keep looking. We didn't try any fractions here, so let's try x equals 1/3. If I try x equaling 1/3, 1/3 squared is that greater than or equal to x? And all these I could put a little question mark because I'm trying to figure out if this is true or not. So I'm wondering, is 1/3 squared greater than or equal to x? Well, 1/3 squared is 1 squared over 3 squared. That's 1/9. Is 1/9 greater? Oopsie. 1/3, is that greater than or equal to 1/3 is what I'm checking. And is 1/9 greater than or equal to 1/3? No, it's not. 1/9 is smaller than 1/3. So this is false. So this right here is our counterexample. Slide this down. So this here is our counterexample. And that means that this statement, x squared greater than or equal to x, is a false statement. Again, all you have to do is find one counterexample to disprove a conjecture. What about this one? Supplementary angles are adjacent. Is that true, or could we find a counterexample to disprove this one? Supplementary angles are adjacent. Well, there's lots of ways that we could draw supplementary angles. We certainly could draw them like this, forming a linear pair. So angle 1 and angle 2 here form a linear pair. They're supplementary and they are adjacent, so that's not a counterexample. But if I draw an angle, let's say like this, and let's say this angle measures 140 degrees, and let's say over here I've got this angle that measures 40 degrees. I'll call this angle A and this angle B. Well, angle A and angle B are supplementary, but they're not adjacent. They do not have a common vertex and a common side. So right here, this would be my counterexample. And in that way, I'm proving that this statement is false. How do I know it's false? Because I found a counterexample. All right, so that's it for this lesson. You're going to be bringing your video guided notes to class to show us for your homework points, and we will have some group work for you on section 2.1 in class. Thanks for watching. Have a great day.